focusing on how you can use DesignBuilder's new sensitivity analysis tools and how they will help you to simplify and speed up optimization studies. I'm Dave Cocking, and with me today are Andy Tyndale and Nishesh Jain. Nishesh is a registered architect who was based in New Delhi in the early part of his career, but more recently he's been undertaking doctoral research with UCL in London and has been heavily involved in the development of DesignBuilder's new uncertainty and sensitivity analysis tools. This webinar will build on the previous one where we introduced the new uncertainty and sensitivity analysis tools. Through using a case study building, Nishesh will draw out some really important points for you to consider relating to the practical use of DesignBuilder's sensitivity analysis. And we hope you'll gain a lot from Nishesh's extensive experience in this field. You can submit questions at any point during the webinar via the questions box in the control panel. We expect the presentation to last around 45 minutes or so, and we've allocated time at the end to answer as many questions as we can. The webinar is being recorded, so you can access it later if required. I'll now hand over to Nishesh, who will be the main presenter for this webinar.
Hi, in this webinar, we will look at how the new sensitivity analysis can be used to simplify and speed up optimization studies and enable a robust design stage decision making in a case study example. We will also show how custom scripts can be used to add significant capability and flexibility in defining the optimization problems. We will be using an internal beta version of the software for this webinar as we intend to show some upcoming new functionality. You might find some of the interface features might not be consistent with the publicly available version 6.1. The webinar is divided into 4 sections. First, we briefly look at the background of the optimization problem, followed by an overview of our case study building. Next, we show how to set up the optimization problem, where we will look at the use of the new custom scripting tool. After this, we will show a workflow where sensitivity analysis is done to simplify the design problem, and then another simplified optimization is completed. Finally, we compare the simplified optimization results created after the sensitivity analysis against a more complex full model optimization to illustrate the benefit of sensitivity analysis. The emphasis of this webinar is to show the advantages of using sensitivity analysis with optimization. Therefore, due to time limitations, we will keep our focus on the processes and the comparisons, not on the case study results themselves. We will be publishing the detailed optimization result analysis of this case study building, which will be available on the website. First, the background. Design stage decisions must balance many constraints and objectives. While some are related to functional, operational, and maintenance requirements, others are more immediate, such as project budgets and regulatory compliance. One of the critical challenges in design stage decision making is value engineering of energy efficiency measures due to cost. Therefore, to ensure that the impact of value engineering on energy efficiency measures is fully understood, there is a need to identify, quantify, and understand which energy efficient solutions have the lowest cost. We must analyze all possible combinations of all design variables that are affected by energy conservation measures to find the optimal solutions. The downside of this analysis is that all possible design variation combinations can lead to a very large search space. 10 design variables with 10 options means more than 10 billion combinations. Optimization using genetic algorithms simplifies this. GAs efficiently identify the best solutions considering the set objectives, which can be presented along a Pareto front. Sensitivity analysis, which are the most determines which are the most influential design variables and what are their relationship with the output. Based on the sensitivity analysis findings, users can remove non-influential variables from the optimization runs. If the variable is influential for only one of the objectives, its value can also be predetermined with sensitivity analysis and removed from the optimization. Therefore, with a focus on only important variables, the optimization results are cleaner, quicker, and easily understandable. Another advantage of using sensitivity analysis is that it helps you to understand any trends associated with the design variables and makes it easier to see these in the optimization results. Now we look at the case study building to understand the optimization problem. The project is located in southern India. Located within the tropics, the climate is hot and humid, with the hottest periods during March and May, with monsoon rains between June and October. Therefore, with regards to energy consumption and comfort, cooling energy use is the most important factor. The project is a 4-story, 5,300 square meter teaching building in a college campus. The main spaces include teaching areas, labs, and staff and faculty rooms. The building form and some of the design features were dictated by the master plan. There is a central corridor with teaching rooms on either side. However, it has a less than ideal orientation. Longer facades are facing east and west. As cooling is the predominant energy end use, this study aims to optimize the fabric and systems to minimize both cooling and capital cost. The design variable options available in this project are related to construction assembly, external finishes, shading design, and space conditioning and lighting systems. The objectives therefore will be minimizing the cooling demand and minimizing the capital cost. These will be our design variables. The question that we want to answer through this analysis would include: can the cost of the HVAC system be reduced by having a more effective envelope? What is the most efficient shading strategy, and can it be traded against the need for a high performance glazing solution? These are the various design variables and their respective options. Envelope construction looks at the intended thermal performance and has options based on varying insulation thicknesses in the walls and roof. The issue of thermal mass is also explored by changing the location of insulation in the external walls and also with varying the thicknesses of the brick partition wall. The window construction focuses on the U value. Various shading options deal with direct solar gains. Shading has a low-cost way of reducing gains and can be used as a trade-off against more expensive glazing solution. Besides U value, another option related to the wall is regarding the external surface finish. Solar absorbance of the outermost material was taken as the variable. Reflective surfaces reduce the cooling energy use significantly and can be achieved at almost no cost implication. However, they are more difficult to maintain and might not be aesthetically desirable. On the system side, lighting is a source of significant heat gains, and selection of HVAC system also presents a trade-off between capital cost and efficiency. The options used here were those selected by the designers, factoring in operations and maintenance issues as well. All possible combination of design variables selected result in a search space of over 1 billion options. If each simulation is 20 minutes, then even with 30 simulations running in parallel, the total time needed would be over 1500 years. However, with GA-based optimization, useful results were calculated in 3000 simulations, taking about 36 hours. Now we move to the second part to see how the relevant design variables were created in the design builder. Then we will look at how the custom scripts can be used to modify any input field and treat it as design variable. At the end of this section, we will discuss the performance trends associated with different variables in this full optimization exercise. This is the case study building model that has been created using architect's initial design drawings. We can see the longer faces run along east and west direction, and there is a central atrium for daylight penetration in center of the building. I'll now go to the edit screen to show some of the model settings in more detail. If we navigate to the ground floor block, we can see that the building has a central corridor with rooms on either side. You can clearly see the atrium here. Circulation, office, and teaching activities have been assigned to various spaces, as you can see from the color-coded key or on the layout. Now I'll go back to the building level. In this project, the layout and activities are fixed according to the design specification, but there is a scope to improve constructions, shading, lighting, and HVAC. So as we saw, these are our all design variables in this exercise. I am not going to review the model data tabs, but instead will show you in the optimization setup dialog some of the key data such as constructions that were used as design variables. After the baseline model is complete, the next step in optimization is to define the objectives and the design variables. This is done on the optimization and uncertainty sensitivity analysis setting dialog, which can be accessed from the toolbars above. On the analysis type tab, we select the type of analysis, in this case, optimization. On the objectives tab, both the design objectives are defined. Design objectives for this case study are minimizing capital cost and minimizing cooling demand. However, there are numerous other KPI options related to comfort, environment, or even unmet loads, which can be used as objectives in various optimization exercises. The Design Variables tab shows all the variables that I have set up for this analysis. For example, external wall U value. I will open it by using the tools on the right-hand side info panel. If I look at the construction options, there are 11 options selected. Here is the list of the construction options. We can see that 11 constructions have been created for this analysis and have been selected as design variable options. Besides wall construction, DesignBuilder has a vast list of variable types in different categories. Custom EMS, custom IDF, and custom scripts are the new ones. They have been integrated to work with optimization in version 6. I have used custom script to create a design variable to show in this exercise. I will now go back to the optimization settings dialog to discuss the custom script design variable in more detail. These are the two design variables created for using custom scripts. Custom scripts can be used to directly modify any aspect of the model, including individual model data input fields. Let's discuss its application in the context of this webinar. I explained earlier that there were two properties related to the walls that were changing. One was related to changing the position and thickness of insulation within the wall construction, the 11 construction options we just saw, and the other one was 5 options for different external surface finish. One of the methods to assess this in the optimization could have been to have 55 wall constructions, pairing each of the surface finish options with each of the wall construction options. However, that would make the interpretation of your optimization results very complex. Custom scripts enable us to simplify this by using surface finishes as one variable and external wall construction as another. Separating the variables in this way means that we can see the impact of both parameters separately when we look at the optimization results. Using custom scripts here, I can select solar reflectance of the outermost material layer as a variable to represent the change in the external surface finish. I'll now show you how to set up a custom script design variable. Let us look at this wall solar absorptance variable named wall sol abs. There are two things that need to be defined here: a unique name for the variable and an appropriate range and step. The name is important here because it will be used by the custom script to identify the variable. I have set the range and step values in accordance with the architect's material specifications. Now the next step is to check the actual data item that is going to change. That is the solar absorptance of the outermost layer of the external wall. If I go to the constructions tab, then there I can see the outermost layer of the construction assembly is defined as wall finish. And the design variable that our script will modify is the solar absorptance value highlighted here. You should create user-defined materials in the model when you are using scripts and changing their properties. The reason for this is that unlike normal modeling, where you cannot edit logged library data, the script will allow you to change it. So if you use your own custom items, then it avoids unintended messing up of DesignBuilder library items. Now the final step for custom script definition is the script itself. Scripts are defined in the scripts manager, which can be accessed from the toolbar above. Scripts can be written in C# or Python programming languages. This is the C# script used in the model. I can open it to see. Scripts like this one unlock the DesignBuilder's API for modification and can be used to set any available API environment property. They use hook points typically before and after simulation to either modify the default IDF generation by DesignBuilder or to access DesignBuilder model inputs to modify or control them. Also, they can access output data to produce custom reports. It is better to explain parts of this script on the slides so that I can easily highlight the part as I discuss. The highlighted part of the script is the hook point, which is called when the design variable changes. It is the point where the script will start making its changes. At this point, the script looks for the optimization variable name. It is looking for our unique variable name, which was wall sole apps. After selecting the intended variable wall sole apps, this part of the script finds the material called wall finish. Then this sets the value of solar absorbance of wall finish to the value that has been chosen by the optimization engine. Scripts can also be written in Python, which may be your preferred programming language. This is an example of the script written in Python. Now back to the model. DesignBuilder help contains extensibility tools user guide, and it can be accessed in the help file here. This is a great resource of help for creating scripts and plugin development. I will now close the script and recap the design variable list by going back to the optimization settings dialog. Now I have already reviewed the design variable for wall construction and for wall solar absorbance. Similarly, as wall construction, variables for roof, glazing, partition, HVAC, lighting, and shading for each of the facades was also defined. Please note, most of the design variables have building as the target object. However, shading has different design variables for each of the facades. DesignBuilder allows users to custom select parts of the model as target objects. So, for shading, the appropriately oriented walls have been selected as targets. DesignBuilder help and the website contains vast resources including tutorials and webinars which you can use to learn the optimization setup process in further detail. Now the optimization setup is complete and we can go to the simulation screen and start the analysis. To start a new calculation, I need to press the Update Calculate Data button. In this calculation options dialog, we define the parameters for the simulation run. The dialog is divided into three sections: the settings selector, the graph window, and the simulation grid. All the settings are defined on the left, and once the simulation has started, after each generation, the graph is populated on the right. For optimization, we can define the number of generations here. This value usually reflects the size and the complexity of the analysis. Program help can be used to understand this in more detail and along with other advanced settings. As all is set now, the optimization simulation can be started. However, as this simulation will take time to finish, I have compiled all the results in the slides. This is the finished result screen. The complete optimization ran for over 3,000 simulations and took about 36 hours. And it has a lot of information which we can analyze, informing designers of various options they can choose. However, the emphasis of this webinar is to show the benefit of using sensitivity analysis with optimization over this traditional optimization method. It is important that therefore results for both the approaches are compared on a like-for-like basis. The sensitivity analysis approach is much faster, and if optimizations were run for indefinite amount of time, then they would have almost the same results. Therefore, to present a true picture of the efficiency and effectiveness of both approaches, we need to compare the results generated within an acceptable time limit. Instead of assessing the final results of both approaches, an equal maximum time limit was applied to each approach. 12 hours was selected as the cutoff time. This will mean that we will terminate the simulation at the end of 12 hours and then compare the results. This is the result screen when the simulation was stopped at the end of 12 hours with just over 1,000 simulation runs completed. The results look significantly less stable at this point compared to the final ones. There are many Pareto points yet to be found. We will now focus on some of the result trends and cluster analysis, which will later be useful in comparison against the simplified optimization run. We'll now look at some of the key points associated with this full optimization set at the end of cutoff time of 12 hours. The total capital cost is shown on the x-axis and cooling energy on the y-axis. Each dot represents each of the 1,000 design solutions simulated. The red dots show the solutions that occupy the Pareto front. The first most obvious pattern I wish to highlight is these four big clusters that point towards different HVAC systems. You can see from this that an improvement in system efficiency has a significant impact on cooling energy use with a relatively modest increase in cost. Second, within each HVAC system cluster, we have three lighting system subclusters. For example, in this VRF cluster on the Pareto front, we can see the impact of CFL, T5s, and LEDs is much greater in cost than on cooling energy demand based on the costing information of this project. At this point in the optimization, due to many design variables, it is difficult to isolate trends and attribute them to specific variables. However, we were able to analyze some of the effect of change in insulation and thermal mass, which suggests adding more insulation or thermal mass has minimal effect on cooling, but only increases cost very significantly. Relative trends of glazing versus shading were the most difficult to analyze because in most of the cases, 2 to 3 variables were changing at the same time, such as glazing, shading on one of the facades, and solar absorptance values. For the shading, some of the trends found suggested we could achieve high energy reduction impact for relatively low cost. Assessment of which shading works best for which facade based on this analysis was inconclusive and required many more data points. So besides the computational effort, the two main drawbacks of analyzing complex optimization results are that first, in this optimization, 12 design variables, each with numerous options, was selected. It was difficult to find clearly distinguishable trends for every variable. Some variables that might not have a significant influence make the assessment of relative importance of other important variables difficult. In this third section, we will look at an alternative approach that will help us to simplify the complex optimization problem. We will use sensitivity analysis to assist in the process. Sensitivity analysis results show which design variables are the most important and which design variables are not. It can also tell us that what is the relationship of each design variable with its objective, if they are directly or inversely correlated. That is, checking if the increase in the variable value leads to an increase or decrease in the objective's value. Combining the sensitivity analysis results of both the design objectives can help find important design variables, thereby potentially reducing the model complexity. The setup for design sensitivity analysis in DesignBuilder is very similar to the optimization setup, but there are some additional important considerations. This is because, unlike optimization, the idea for sensitivity analysis is to understand the relationship between design variables and the objectives, and not to find the best answer. I will show them within the modeling environment. I have to change machines to open the new file. This is exactly the same model with sensitivity. This is exactly the same model with sensitivity analysis settings configured to assess the cooling electricity objective. All model details remain the same apart from the analysis settings defined on the optimization and uncertainty and sensitivity settings dialog. I will review them now. On the analysis type tab, we can see that the analysis type has changed from optimization to uncertainty and sensitivity analysis. On the outputs tab, the output is defined as cooling electricity. We do not have capital cost, our other objective, as an output here. It has been analyzed separately. This is because in sensitivity analysis, the order in which design variable options are selected is very important. They need to be ordered in an increasing or decreasing value. For example, if U value of the wall is changed by using different materials, then the wall option sequence, when ordered in decreasing U value, might not be corresponding with the one created with increasing capital cost. In those cases, sensitivity analysis must be done separately. While theoretically sensitivity analysis could be done for both objectives together, it is generally a good practice to set them up separately. On the design variables dialog, there are further differences that I'll point out compared to the optimization setup. Let's look at the wall. Sensitivity analysis requires a definition of probability for any option for a particular variable occurring. I can see that probability distribution graph by creating update graph button. The existing distribution is a uniform distribution, which means that all options are equally likely to be selected. The other thing to note is that there are 5 options here ordered in increasing U value. The lowest U value having the maximum insulation is the first one, and the highest U value with no insulation, the last one. The 5 options here is lower than the 11 options we used in the original optimization. This is because some of those were not suitable for this sensitivity analysis due to the nature of methods used for calculating sensitivity in sensitivity analysis. The sensitivity analysis focuses on the construction U value. Excluding the six wall options, the excluded six wall options were duplicates of the currently selected ones. We were just looking at their U value. A variant with only the change being location of the insulation. Sensitivity, their analysis does not work efficiently if the duplicates are part of the sequence. More information on other distributions and overall design variable setup for sensitivity analysis is available in the program help. The last difference I want to highlight is that we don't have the HVAC system design variable. The HVAC system is a very influential variable for cooling energy, so much so that it dwarfs every other factor. In my initial runs, I found that HVAC system was skewing the sensitivity analysis, and the confidence level values in the results of other variables was not very high. A sensitivity analysis with significantly larger number of runs could have brought them within the acceptable limits, but it was more practical to do an analysis without the HVAC system design variable. In subsequent results, we can then reinstate the HVAC system as the most significant variable. A bit of a sneak preview here. We use custom scripts with sensitivity analysis, like we saw with optimization. This is a new feature coming in version 6.2. I am using the 6.2 beta version, and therefore I was able to include this in the sensitivity analysis. Now that all design variables have been reconfigured, we can go into the simulation screen to do the analysis and look at the results. In the interest of time, I have already completed the simulations and have the sensitivity analysis results ready for visualization. The results show the relative importance of each of the design variables for cooling demand. They are ordered in decreasing order of importance, which is determined by the standardized regression coefficient value. The confidence level of the analysis is very high because of the high R-squared value and low p-values for all the design variables. The report explains this fully, but R-squared and p-values are key indices related to confidence in the model. Roof solar absorptance, glazing, lighting, wall U value, partition thermal mass, and shading on east and west facade are the most important variables. A positive value for roof solar absorptance means that increase in solar absorptance leads to an increase in cooling demand, whereas a negative value for shading means that increase in shading results in a decrease in cooling energy use. Sensitivity analysis results are interpreted and explained fully in the report. The report is a very informative document that summarizes the entire simulation results. The numbers that are not very intuitive to understand are explained in detail to assist specialists and new users in interpreting the results more meaningfully. The report is divided into 4 parts. The first 2 parts describe the input and the outputs. The third part provides details about the analysis settings and also lists the uncertainty results. Most importantly, in the last part, the report provides interpretation of the results and graphs, statistical details, identifying the most important and influential parameters. If I scroll down to the end of the report, I can see that the sensitivity analysis numbers such as adjusted R-squared values, p-values, standardized regression coefficient values are interpreted in plain English. The most important variables are ranked and color-coded. Similarly, for sensitivity analysis, like for energy, the cost and sensitivity analysis was also created, and a ranking list of the most important variables also created. I will move back to the slides where I will be comparing these importance rankings of design variables for both the objectives to understand which of the design variables can be removed from the optimization to make it simpler and faster. These are the two sensitivity analysis graphs, one for cooling energy and one for cost. We can clearly see that some of the variables are more important than the others, and the ranking order is also different for the two objectives. A point to note is some of the variables have not been analyzed in these analyses. While the removal of HVAC system for cooling energy was explained earlier, roof and wall solar absorptance did not have any significant cost implications and therefore were not analyzed in the cost sensitivity analysis. These are the sensitivity analysis results listed for cooling energy and cost, highlighted based on their level of sensitivity. Low, medium, and high are marked in red, yellow, and green colors respectively. Now we see the process to select the variables for a simplified optimization based on these sensitivity analysis. This is the decision matrix that was followed. The key points are that if a design variable has high or medium importance for both the objectives, then the sensitivity results then it should be kept in the simplified optimization. If it has low importance for both the objectives, then it can be removed and the designers can choose any suitable option. However, if design variable has high or medium importance for one objective and low importance for another, then it can be removed from the simplified optimization as well. However, the recommended value of that variable will be based on the sensitivity analysis results. It will be the value which best meets the objective for which it is most sensitive for. So for the simplified optimization in this exercise, we keep the wall U value, roof U value, window U value, and partition thermal mass design variables for the following optimization exercise as they are important for both the objectives. On the other hand, shading on north and south facade are not important for either cost or cooling energy, most probably due to smaller number of windows on those facades, so they can be excluded in the simplified optimization. On this basis, the architects are free to select any shading for those facades that meet the aesthetic requirements. East and west shading have high importance with respect to cooling, but low importance with respect to cost. Therefore, remembering our conclusion from sensitivity analysis, increasing the amount of shading in the specified range would reduce our cooling energy. So we can recommend one of the larger shading options for those facades and also remove them from the optimization. Similarly, for surface finishes, as they have low importance for cost, a light reflective coating, which is better for cooling energy, can be selected for this option and removed from the simplified optimization analysis. Light and HVAC system affect both objectives and must be kept within the simplified optimization. Therefore, for the final simplified optimization, we have reduced the number of variables from 12 to 6. The green ones are included and the gray ones have been removed. The search space has reduced drastically to the extent that even a full parametric analysis is practically possible. However, for this analysis, we took a very robust optimization which took about 9 hours. Adding the 3 hours that took for about 200 simulations done for sensitivity analysis, the total simulation time was 12 hours, exactly the same time as the cutoff time for this comparison against the full optimization results done earlier. In this section, we will look at the results of the simplified optimization and compare those with the results which we had previously for the optimization run stopped after 12 hours. In other words, we are looking at the results of both approaches at the end of 12 hours, having done about 1000 simulation runs each. Just to reinforce the point, we have run 2 optimizations for this webinar to illustrate the benefit of using sensitivity analysis to simplify and speed up the optimization process. This is the screenshot of the completed simplified run. The results look visibly cleaner. There is significantly reduced noise compared to our previous full optimization, which was coming from the unnecessary variation in shading and solar absorptance values. These were the non-influential variables that were removed after sensitivity analysis. By placing the 2 optimization results side by side and looking at the same clusters and trends looked at earlier, you can see that the simplified optimization results are more meaningful and easier to interpret. First, the HVAC system. We can clearly see that there are 4 distinct clusters for each of the HVAC systems. Moving on to the lighting system, the subclusters for different lighting types can also be seen, which may help you give confidence that all the simplified results have not lost any of the value. The quality of data needed for understanding the effect of increasing insulation or thermal mass on the cost has increased significantly. On and around the Pareto front, we can not just see the hints of trends, but many intermediary combinations. Most significant difference is seen with regards to glazing. As noise from shading options gets eliminated, it is possible to analyze the impact of increasing U value on cost and cooling very efficiently. These trend lines show increasing U values for glazing with different roof insulations. The offset of the 2 lines is because of the roof insulation, and we can see the diminishing returns in cooling energy with adding more expensive, better U value glazing. This type of analysis for glazing was very difficult in the full optimization results, which we had at the end of 12 hours. The same time it took us to do both the sensitivity analysis and the simplified optimization. So in conclusion, use of sensitivity analysis makes the simplified optimization more effective and significantly reduces overall simulation time. Sensitivity analysis helps us to identify and eliminate design variables that were unimportant for one or both the objectives, or to reduce and refine the search space significantly. Despite removing many design variables, there was no effect on the quality of the analysis that could be done. All relevant trends and patterns could be found. This was supported by the fact that the simplified optimization results were visibly cleaner and had more refined Pareto fronts. This made the trend and pattern analysis much easier to understand and significantly faster to process. This is the end of the formal presentation. Thank you.